we want to take this function and rewrite it as a power series. If it's a power series, that means it should look like this. Some constant a sub 0 plus a different constant a sub 1 x minus c plus a different constant a sub 2 x minus c squared, and then it keeps going, right? A sub 3 x minus c to the third. And so a quick way of writing that is the sum from n equals 0 to infinity of a x minus c, sorry, a sub n x minus c to the nth power. So that would be a power series representation. So what it's doing is it's taking this function and rewriting it in series notation, basically. Okay, so if you go infinitely in this function, you should be able to match what's happening. If you go infinitely in this series, you should be matching what's happening in this function. So a new way of looking at the function. And so in order to do that, what we often have to do in our problems in our textbook are we have to look first at a geometric series. Okay, so a geometric series says you have some number times a common ratio r. And so it's geometric if you're always multiplying by the same number, which is the same as dividing, because if you multiply by 2, that's the same thing as dividing by 1/2. So you could put fractions in there in division if you want. So that's a geometric series. So we want to try to rewrite this so that we can think of it as a geometric series. And geometric series have a nice property that if you're summing all the terms to infinity, the sum of the terms as we approach infinity is a over 1 minus that common ratio. Okay, so this looks pretty similar to what we have over here, right? We could factor out that negative 13 if we had to, but we just need to rewrite it so that it's 1 minus x instead of x minus 1. So that's pretty easy to do. And same thing over here, we could easily rewrite that as a sum of a geometric series. So up here, if I factor out a negative 1 from the numerator, that will give me the signs I want. So we've got 13 over 1 minus x, and then over here x plus 1. We can rewrite that as a negative x, because that means a positive x. And so that allows us to rewrite as 1 minus something as well. So this is 1 minus negative x. And so now that it's in this geometric form, we can rewrite it as the sum of an infinite amount of terms in a geometric series. So we have 13 for our a for this one. 13 was our a. Then it's 1 minus r. In this case, r is x. So we're going to put x to the nth power. Sum that from n equals 0 to infinity. So we've got that in series notation. And then over here, a is also 13. R is just negative x to the nth power. And there's a way we can deal with that, because n equals 0, then this is going to be a positive number. And n equals 1, this is going to be negative. And n equals 2, this is going to be a positive number. So the tradition, the convention, is to rewrite that as something that clearly identifies it as an alternating series. You can say negative 1, what's the first term? If you plug in 0, you get positive. So this should be n times 13x to the nth. This and this are the same thing, right? It's like I factored out that negative 1. And since they're both summing from n equals 0 to infinity, we can add these as one big series. Can factor out a 13 from this term and from this term. I'm left over with, I can factor out a 13 and an x to the n. And I'm left with 1 when I factor out 13x to the n. And then over here, I've got my negative 1 to the nth. And I think that's it. So this is pretty much this form up here. We need an x to an n power, so we could just rewrite that off to the side to make it match in terms of the order that we wrote up there. So this is 13, 1 plus negative 1 to the nth, x to the nth. So in our series, c is 0, right? This could be this could be x minus 0 to the nth power. So c is 0, and our a sub n term is all this right here, this computation. So now it's a power series representation.